How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
Imagine you are sitting in seat 14A on a transatlantic flight 35,000 feet above the Atlantic Ocean. Outside your window, a massive jet engine is roaring, sucking in cold air and turning it into thrust. It looks steady. It sounds consistent. You trust it because it feels like a solid, unchanging piece of machinery. But miles away, in a quiet, climate-controlled server room, that exact engine is also flying. It is spinning at the same RPM, experiencing the same vibration, and enduring the same intake temperature. This second engine, however, is made entirely of code, and 10 minutes before the real engine outside your window develops a hairline fracture in a turbine blade, the code engine breaks. A light flashes on a dashboard in a maintenance center in London. The ground crew knows the engine is failing before the engine knows it is failing. We assume our machines are isolated objects that only tell us they are broken when smoke starts pouring out. But how does a collection of sensors and software actually clone a physical object in real time? How do we build a bridge so precise that the digital ghost can save the physical body? Today, we are peeling back the layers of the digital twin. To understand the magic of the digital twin, we first have to look at the sheer scale of the illusion. This isn't just about jet engines. Right now, there is a digital version of the entire country of Singapore. It is not a map. It is a living, breathing organism of data. In this virtual Singapore, officials can simulate a flood to see exactly which basements will fill with water. They can simulate a new skyscraper to see how its shadow will affect the solar panels of the surrounding buildings. They can even simulate a flu outbreak to see how people moving through the subway system will spread the virus. This is the promise of the technology. It allows us to treat the real world like a word processor. You know how you can type a sentence, realize it is wrong, and hit undo. You can't do that with concrete. You can't do that with a failed heart valve. You can't do that with a crashed car. But if you have a twin, a perfect shadow of the object, you can crash the twin 1,000 times to make sure the real one survives. It feels like a superpower. It feels like we have finally conquered the unpredictability of matter. But the term digital twin is thrown around marketing departments with reckless abandon. It sounds sophisticated. Like the next evolution of a 3D model, we look at a spinning graphic of a car on a screen and think, that is it. That is the twin. But visually representing an object is the easy part. We have been drawing blueprints for centuries and making 3D models for decades. The magic isn't in the picture. The magic is in the timing. The problem that birthed this technology is as old as engineering itself. It is the problem of the unknown variable. For most of human history, if you built a bridge, you didn't know if it would stand up to a specific windstorm until that windstorm hit. You could do math. You could build small-scale models. But reality is messy. Reality has rust. Reality has metal fatigue. Reality has bird strikes and unexpected thermal expansion. The map is never the territory. Engineers have always been desperate to bridge this gap. They wanted to know what was happening inside the machine while it was running, without having to stop it and take it apart. Because usually, by the time you take it apart to find the problem, the damage is already done. This desire reached a fever pitch during the space race. Let's go back to April 1970, Apollo 13. We all know the line about Houston having a problem. An oxygen tank exploded, crippling the service module. 3 astronauts were stranded in a dying tin can halfway to the moon. Back in Houston, the mission control team faced a nightmare. They needed to power up the lunar module to use as a lifeboat, but they had to do it with a battery budget that was razor thin. If they flipped the wrong switches in the wrong order, the system would spike, the batteries would drain, and the astronauts would die. They couldn't test it on the ship. They had one shot. So what did they do? They didn't have a digital twin. Computers back then were the size of refrigerators and had less processing power than a singing birthday card. They couldn't simulate the physics in code, so they used a physical twin. NASA had built exact physical replicas of the command module and the lunar module on the ground. These simulators were wired exactly like the ships in space. When Ken Mattingly, the astronaut who had been bumped from the flight, climbed into the simulator in Houston, he wasn't looking at a screen. He was flipping real switches. He was watching real gauges. He spent hours trying different startup sequences on the ground, sweating through the procedures, failing, resetting, and trying again. He was crashing the twin to save the ship. This was the grandfather of the concept. It was a mirrored system. But it was analog, it was slow, and most importantly, it was disconnected. The simulator on the ground didn't know what the ship in space was doing unless an astronaut radioed down the numbers. Ken Mattingly had to manually set the switches to match what the crew reported. There was no invisible thread tying them together. As computing advanced, we moved from physical mock-ups to computer-aided design, or CAD. We could build a bridge in a computer. We could look at it from every angle. We could even run a static simulation, applying a theoretical load to see if the theoretical beams would hold. But a CAD file is a dead thing. It is a snapshot in time. It represents the object as it was designed, not as it is. A CAD file of your car doesn't know that you hit a pothole on Tuesday and knocked the alignment off by 2 degrees. A CAD file doesn't know that the oil filter is clogged. This was the fundamental limitation. We had the blueprint, but we didn't have the biography. We needed a model that aged. We needed a model that suffered. So, let's open the black box. How do we turn a static file into a living twin? The core analogy here is not a portrait. A portrait captures you at one moment and stays beautiful forever, even as you age. That is a 3D model. The digital twin is more like a voodoo doll, but one that works in reverse. In the movies, if you stick a pin in the doll, the person feels it. In a digital twin, if the person gets a cut magically appears on the doll. And if the person gets a fever, the doll gets hot. The connection must be continuous, and it must flow from the real to the virtual. This brings us to the first principle of the digital twin, the sensor layer, or the nervous system. To create a twin, you cannot just model the shape of the object. You have to instrument the object. You have to cover it in digital nerve endings. Let's go back to that jet engine. A modern engine from General Electric or Rolls-Royce is fitted with hundreds, sometimes thousands of sensors. They measure pressure, temperature, vibration, airflow, fuel flow, and acoustic resonance. Every second, these sensors are generating a torrent of data. They are the eyes and ears of the system. This is where the Internet of Things, or IoT, comes into play. Without IoT, the digital twin is impossible. The object must be able to speak. It must be able to broadcast its internal state to the world. But raw data is just noise. Knowing that sensor A reads 400 degrees and sensor B reads 500 degrees doesn't tell you anything unless you have a structure to put it in. This leads to the second principle, the virtual counterpart, or the body. This is the 3D model we are used to seeing, but it is beefed up with physics. It is a container for the data. The software takes the geometry of the engine, the curves of the blades, the thickness of the casing, and applies the laws of physics to it. It knows that if the temperature goes up, the metal expands. It knows that if the vibration hits a certain frequency, the bolts loosen. When the data from the sensors hits the virtual counterpart, the model updates. It doesn't just display the number 400 degrees. It simulates the thermal stress on the virtual metal caused by that 400 degrees. The virtual engine effectively mimics the pain of the real engine. Now we have a body, and we have nerves, but we are missing the most critical part. We are missing the brain that connects the two distinct timelines. We need to understand the flow of time. This is the third principle, the temporal loop. A standard simulation predicts the future based on a theoretical past. A digital twin predicts the future based on the actual present. This loop creates a constant conversation. The real object says, "I am vibrating at 50 Hz. The digital twin takes that input, runs it through its physics engine, and says, "Based on my geometry, if you are vibrating at 50 Hz, it means bearing number 3 is loose." This is the aha moment for the maintenance crew. They can't see bearing number 3. It is buried inside the machine, but the twin can infer the internal damage based on the external symptoms. It creates visibility where there was blindness. But the loop goes further. Once the twin matches the real state, it can detach itself from the present and run fast forward. This is where the time travel happens. The computer says, "Okay, bearing 3 is loose. If we keep flying like this for another 5 hours, what happens?" The digital twin then runs a simulation into the future, accelerating time. It simulates the next 5 hours of flight in a fraction of a second. It sees the vibration increasing. It sees the heat building up. It sees the bearing shatter. It sees the catastrophic failure. And it reports back to the present. You have 4 hours until failure. This distinction is crucial. It is the difference between a check engine light and a crystal ball. A check engine light tells you that something has already gone wrong. A digital twin tells you what is about to go wrong. Let's pause on a specific example to ground this: Formula 1 racing. An F1 car is perhaps the most advanced example of this technology on the planet. The car you see on the track is covered in over 300 sensors. It transmits gigabytes of data every lap. But the team isn't just watching the telemetry. Back at the factory in the UK or Italy, there is a driver-in-the-loop simulator and massive server banks running a digital twin of the car. During the race, the real car is dealing with tire degradation. The rubber is wearing down, the track is getting hotter, the fuel load is getting lighter. The digital twin is fed all of this real-time data. It updates its virtual weight, its virtual grip levels, and its virtual aerodynamics to match the car in Singapore or Monaco exactly. Then the strategists ask the twin questions. What happens if we pit now for hard tires? What happens if we stay out for 5 more laps? The twin runs thousands of races in parallel, simulating every possible outcome based on the current reality of the car's condition. It plays out the next 20 laps 1,000 times in a few seconds. The team looks at the probabilities. If we pit now, we have an 80% chance of coming out ahead of the Ferrari. They make the call based on a future that hasn't happened yet, but which the twin has already experienced. This sounds flawless. It sounds like we have solved engineering. But if you talk to the people who build these systems, they will tell you that the hardest part isn't the sensors, and it isn't the 3D graphics. The hardest part is the one thing we haven't discussed yet. It is the unseen giant of digital twins, context. We tend to think of machines as isolated systems. A jet engine is a jet engine. But a jet engine flying through a sandstorm in Dubai is a different machine than a jet engine flying through clean air over Antarctica. A car driving on a smooth German autobahn is different from a car driving on a potholed street in Chicago. To build a truly perfect digital twin, you cannot just model the object, you have to model the world around the object. This is the non-obvious principle, the boundary condition problem. If your digital twin of a wind turbine is perfect, but your data about the wind hitting it is wrong, the prediction will be wrong. If you have a digital twin of a human heart, but you don't account for the stress hormones in the blood caused by the patient's anxiety, the model will fail. The unseen giant is the environment. Early digital twins failed because they were narcissistic. They looked only at the machine. Modern digital twins are successful because they are humble. They realize the machine exists in a chaotic universe. This requires a massive integration of external data. The twin of the jet engine doesn't just listen to the engine sensors. It connects to global weather APIs to know the humidity and particulate matter in the air. It connects to the flight plan to know the altitude. It connects to the maintenance logs to know when the oil was last changed. It turns out that to simulate one thing perfectly, you eventually have to simulate everything in its vicinity. This is why the technology is so difficult and expensive. You are fighting the butterfly effect. Small changes in the environment can have massive effects on the system, and if your twin is blind to the environment, it will drift away from reality. This drift is the enemy. If the digital twin says the temperature should be 500 degrees, but the real sensor says it is 510 degrees, who is right? Is the sensor broken? Or is the twin's physics model slightly off? Or is there a tailwind that the model didn't account for? Solving this discrepancy involves high-level mathematics and statistical probability. The system has to constantly recalibrate. It has to admit, I was wrong, and snap back to the reality of the sensor data, then adjust its internal logic to understand why it was wrong. This ability to learn from its own errors is what separates a static simulation from a smart digital twin. It is constantly evolving its own internal code to better match its physical brother. So where does this leave us? We are moving into a world where every critical object, bridges, power plants, cars, and eventually our own bodies, will have a silent, invisible partner living in the cloud. This matters because it fundamentally shifts our relationship with failure. For all of human history, we have learned by breaking things. We built a cathedral, it fell down, so we built the next one with thicker walls. We learned through tragedy. The digital twin offers a new paradigm, learning through virtual failure. We can crash the plane, collapse the bridge, and stop the heart 1,000,000 times in the code, so that when we build the real thing, it is already a survivor. It has already lived 1,000 lives. But there is a deeper philosophical shift here. As these twins become more high-fidelity, the line between the map and the territory blurs. If we can run a city more efficiently in the simulation than in reality, we start to govern based on the needs of the model. We have to ensure that in our quest for optimization, we don't forget that the messy, unpredictable, unmodeled reality is the one we actually live in. The twin is a tool to understand the world, but it is not the world itself. The goal of the digital twin is to give us the foresight of a god, but we must wield it with the wisdom of a human. We are building a mirror world to save the real one, and the clarity of that reflection depends entirely on the honesty of the data we feed it. In the end, The digital twin reveals a simple truth: nothing exists in isolation. To understand the part, you must understand the whole. And to save the machine, you must first let the ghost in the machine tell you its story.
You've been listening to First Principles. Until next time, stay curious.